let's see if we can get more general formulas for the moments about the x and y axis of a laminar shape, a thin sheet of material. So let's suppose that our sheet of material, our lamina, has density rho. So this is a laminar density since it's mass per unit area. And we're going to suppose that we've cut this shape or we've arranged for this shape so that it goes from x equals a to x equals b. It's bounded on top by some graph y equals f of x, and it's bounded on the bottom by some graph y equals g of x. Okay, so first let's find the moment about the y-axis. So what we're going to do is, right, this is very much like the handout where we slice this into vertical pieces. Right, so here's a typical vertical slice. We need to integrate the moments of each slice. So we're going to integrate from A to B, and now we just need to write down the moment about the y-axis of a single slice in here. So the distance of this slice from the axis of rotation, which is the y-axis in this case, that distance is x, or I should say that displacement is x. Now we need to multiply that by the mass for this vertical slice. Well, the width of the vertical slice is dx. The height of the vertical slice is f of x minus g of x. And the density of the laminar density of this material is rho. So we need a rho right here. So here's the formula for the moment about the y-axis. Now let's think about the moment about the x-axis. The moment about the x-axis is going to be a little more tricky because, for this shape, we can't slice it horizontally, at least not in a convenient way. Right? Sometimes, if we slice this horizontally, sometimes the left-hand end of the slice is on the graph of g of x, but sometimes it's on x equals a, but sometimes it's on the graph of f of x. So slicing this region horizontally isn't really going to be very practical, at least not for this region with this general shape. So what we'll do instead is let's concentrate just on the part of this region that is the part of this region that's at position x. So we've got a slice here at position x, and the bottom of it is at g of x, and the top of it is at f of x. So let's find the moment about the x-axis just for this slice. So this, I guess, moment about the x-axis at position x. So I guess we should write it like that. So what we're going to have to do is break this slice up into many pieces, because all of these pieces, as we move upwards, they're all at different distances from the x-axis, which is the axis of rotation for our moment calculation here. So to find the moment of a single piece here, we need to take the mass of this piece, which is the laminar density times the area of this piece. But look at this piece. It's infinitely narrow in the x direction, so its width is dx, and it's infinitely short in the vertical direction, so its height is dy. Okay. Now we need to multiply that by the displacement of this piece from the pivot for our moment, which is down at y equals 0. And this displacement, that's just y. Okay. And then we need to integrate this for all of the different pieces along this vertical slice. But along this vertical slice, these pieces go from the bottom, which is g of x, y equals g of x, to the top, which is y equals f of x. Okay, now this looks kind of funny because we have two variables floating around, but for this integral, it's really a y integral because we're integrating from the bottom upwards in the y direction to the top. So for this integral, x is constant. I know that may seem strange because we have a differential of x in here, but we'll see how that comes into it in a second. So since rho is constant, and as far as this integral is concerned, dx is constant, since this is a y integral, we can move rho outside of the integral, and also move dx outside of the integral. I'm going to move the dx to the end of the integral, like this, or outside of the integral on the right-hand side. And we're integrating just dy from g of x up to f of x. Okay, so this is rho times y. I'm sorry, something didn't look right. This y should be in here, so I forgot to write it down right here. So when we integrate, we get 1/2 y squared from f of x, from g of x to f of x dx. And then when we plug in our bounds, we find that the moment about the x-axis of the slice at x is rho over 2 times f of x squared minus g of x squared dx. Okay, so that's the moment of just this one slice about the x-axis. So now the total moment about the x-axis, we have to take this entire expression and integrate it with respect to x, which makes sense because it has a dx in it. So we need to integrate this from a to b. So rho over 2 f of x squared minus g of x squared dx. And so here's a formula for the moment about the x-axis. It might seem a little strange that we get squareds here, but this is reflecting the fact that, or this happens because our cross-sections are all at, each point of our cross-section is at a different distance from the x-axis. Okay, so summarizing what we have so far, if we have one of these shapes, a lamina with laminar density rho, and it occupies from x equals a to x equals b, and bounded on top by f of x and on bottom by g of x, then our moments are the formulas we got. So moment about the x-axis is integral from a to b of rho over 2 f of x squared minus g of x squared dx. And the moment about the y-axis is integral from a to b of rho times x times f of x minus g of x dx. Of course, if you have a lamina of laminar density rho, the mass of the lamina is just, it's the density times the area, but the area of that lamina is the integral from a to b of f of x minus g of x dx. So this piece right here, this integral is just the area of our lamina. And if you want to, you can move the rho inside. So that's where I'm getting this expression from. So now we have a formula for the moment about the x-axis, the moment about the y-axis, and the mass. So now we can calculate the center of mass of one of these things. Just like for individual masses, the x-coordinate of the center of mass is the moment about the y-axis divided by the mass. And the y-coordinate of the center of mass is the moment about the x-axis divided by the center of mass.